Today, we continue with this series of lectures about cryptography. So today our lecturer is René, and he will be talking about new constructions of minimal binary codes. So please, René.
Oh, thank you. Can you hear me well? Everything is fine, right?
Yes, we can hear you nicely.
Yeah.
Okay, thank you for the nice introduction. And I'll also like to thank everyone for joining this meeting, and also the staff at UP and at UP, sorry, and at FAMNIT, and in particular to the organizers of this weekly seminar for having taken charge of everything properly and timely, despite the unusual ongoing situation, right? And it's my very first time here. I'm so happy to be sharing with you a little bit of my research. And I'll be talking about a recent work on minimal codes. And this is joint work with NS Pasalic, Fengrong Zhang, and Yongzhong Wei. Here's a brief summary of the talk. First of all, we'll discuss some basic concepts of block codes and classic constructions of such codes. And also, this is like a brief introduction to linear codes and coding theory in general. And afterwards, we'll discuss minimal codes, which are a specific class of linear codes. And we'll study some properties. I want to describe a specific construction of minimal codes. And we'll do so in the third part of the talk, and where we construct certain families of minimal codes with specific properties. And finally, we'll give some open problems and future discussion, future directions of research. And okay, first off, what's coding theory? Well, and more importantly, what's a code? A code can be roughly described as a set of rules to convert certain amount of information, say video, photos, bits, or whatever it is, whatever source of information, into another form, typically to shorten or to hide it somehow. And this is a very vague definition, but it'll be useful for us for now to have an idea. And coding theory is the systematic study of such codes and their properties, of course, depending on applications. There are different kinds of applications, and we'll see a little bit later some of them. And coding theory branches into mainly 4 areas, which is source coding, and it can be seen as data compression, channel coding, or so-called the error detection and error correction coding, and cryptographic coding, and also line coding. I want to mention here that the error correcting codes are well studied, and I think those 2 that I put in bold are the ones that I'll be mainly focusing, actually only focusing on them. And this error correcting and detection was started in the 1945, I guess, when Shannon started all this theory of information theory, and some more people at the Bell Labs also developed this theory. And further developments of this error correcting were used for cryptographic purposes, and this encouraged research in this direction, and we'll be focused on those 2. First, let me explain some applications. And I think the most prominent application of coding theory is CD-ROMs. So CD-ROMs are in everyday lives. They're everywhere, and they're very important, and they're based on the principle of error correcting codes, which is called the Reed-Solomon code, and was introduced in 1960. And those codes also have important applications in QR codes and data transmission, DVDs, and stuff like that. Also, another important application of coding theory is to the satellites. So specifically to the Mariner program, which was a 10-mission program conducted by NASA. And the purpose of the program was to send the spacecraft to the closest planets and to send images of those planets back to Earth. And the problem was that there was a lot of noise, thermal noise in that transmission. So the solution was to employ an error correcting code to fix those errors. And that was very impressive at the time. And some more applications are hard disk, communication systems, storage errors, authenticity, security, zipping data, and many more. Okay, here, but actually, what's coding? Where are we? Where does coding theory? Sorry?
I'm in Sweden.
Okay, Sweden, I'm in copper. But I mean, coding theory, it belongs to cryptography, to information theory, to mathematics. Well, first of all, I apologize beforehand because the following drawing is very imprecise and it's my personal opinion. And it's really hard to classify a field, a specific field, especially if there are so many interconnections between that field and many other fields. But this is roughly and just for us to get an idea of what's going on, right? So we have here information theory. Can you see the cursor here?
Yeah.
Okay, so we have information theory, we have cryptology here, and we have mathematics all over here. And coding theory is this square over here. And there are some space here for, let's say, implementations which are not relying on mathematics, purely mathematics, right? But we'll be mainly focused on this light yellow area here. Okay, block code. Block codes are a family of codes which are useful for error correcting codes in principle, but they are also useful for some other types of coding theory, such as cryptographic coding theory, right? And a block code is simply a proper subset, C, of another set of the n tuples of a set, and with cardinality m. We call this an NMQ block code, and Q can be any finite non-empty set, and we require that n is a positive integer. So think about as Q. Think of Q as the alphabet, and C is encoding certain information. So n is called the length of the code, and m, of course, is the size of the code. And here's a picture for us to understand it a little bit better. And here, this m is a little bit misleading because this is not the message, but this m is sort of like pieces of information that we can use in on our message. So actually, our message will be composed by taking some elements here in M, and it'll be divided in codes. So every block will belong to M, every block. That's why it's called block codes, because we can divide our message into blocks. Each block belongs to M, and then we encode it using C into this alphabet. Okay, this is the idea. And here's another diagram, which is a little bit more explicit. As I was mentioning, this is wrong because this is not the message, but instead I'll call this like piece of information. So the piece of information here has length 6, and we encode it into our set here. Let's say that Q is the set of 2 elements. So we're working with binary code, and the length of the code will be 2 to the 6 here, and the length the block length will be 32. So we'll have a subset of size 2 to the 6 and with 32 tuples within this codification here. And somehow we want to send it through a noisy channel. Therefore, some errors were added to this code word. We call them code words, and we received a word, some random word. Well, if we received the code word, we can assume that we didn't receive any. There were no errors if we receive a code word. Otherwise, we have a error pattern here, and if we're lucky, then we can decode it, and most likely it will be determined, and then we can decode it and get our original piece of information. Okay, so here there are some questions that I want to touch a little bit, and here is that the decoding is possible using redundancy. Redundancy is this amount of bits. We have 32 bits here compared to 6 bits here. So we have 26 bits of redundancy, which will allow us to decode efficiently, okay? And that's one thing. Another thing is that it's not for free, because we have 5 times more bits to carry and to send through a channel. So it's gonna be 5 times slower, this process. And also it'll consume more energy. So that's where an important measure of this kind of transmission is called the information rate. And it's simply defined as the logarithm with base q of m over n. So this measures the amount of information that has to be sent, kind of, like how can we compare those measures? And so we have here this transmission. And what I wanted to say was that typically the channel is oops, sorry. I wanted to say that Shannon's theory studies all these things related to entropy and energy, and it was like the first mathematical treatment of information, and he based everything on this information rate. And well, there are a lot of nice things over there, and this is important. Okay, so now, and another important parameter of a code is the minimum distance. And the minimum distance is simply defined as the minimum Hamming distance between code words, and the Hamming distance being the number of places where those vectors differ. And then we can compare those code words, and the larger the minimum distance is, the let's say the capability of correcting errors and detecting errors will be larger, or will be more efficient. And
may I pose a question here?
yes, sure.
I mean, so you are defining just the Hamming distance between the code words, but there are other notions. There is a lead distance. There are other kind of concepts, but this is true for binary codes, right?
No. The Hamming distance, I mean, we can define the Hamming distance for every alphabet.
Okay.
Simply as defined as the places where they differ.
Yeah, of course, but in certain cases, I mean, one uses lead distance, which is more accurate measure than the Hamming distance, because it,
Yes, yeah, probably, yes, yes.
yeah, okay, well,
Yeah, okay, so we can define different distances, sure.
yeah. So it's not the kind of that you have to stick with the Hamming distance.
No, definitely not.
Right, okay.
Mhm. Yeah, and but the thing with the Hamming distance is that there are methods, decoding methods, such as the nearest neighbor decoding, and that's the important thing I think about the minimum distance, that we can decode it. Oh well, yeah, actually, you can use whatever metric you want here.
Yeah.
So okay, yeah, but it'll be important for linear codes. Okay. And that's our next topic. And what's in principle, our alphabet Q could be anything we want. But if we endow our alphabet with certain structure, let's say an algebraic structure, we can in principle deduce some more interesting facts. And actually, there are some works working with alphabets, which are a group, for instance, rings or things like that, but we'll stick to the vector space case. And a linear code will be a subspace, k-dimensional subspace of our vector space here. FQ denotes the finite field with Q elements, and it'll be an NKQ code. Note here the brackets. This notation is common in practice to denote this for linear codes, while we denote with parentheses the a priori non-linear codes. And linear codes, because of the linear structure, we can have we can, for instance, decode more efficiently using something called the syndrome decoding, and that's why linear codes are, in a sense, better than just arbitrary codes, right? Because there are a lot of structure. And just for this, I want to explain you, we'll need the weight of a vector. The weight of a vector simply is defined as the size of its support. And this is the places where the vector is non-zero. So that's the weight. And the most impressive fact, or well, probably the most useful fact, is that the minimum distance equals the minimum weight, the minimum non-zero weight of code words. And this is actually very interesting because for computing the minimum distance in an arbitrary code, in principle, we have to perform m choose 2 operations. And here we can use simply m operations. So actually n minus 1. So it's much more efficient. Another important concept is the one of the orthogonal complement. Since we're working with linear things and we have a well-defined bilinear mapping here, then we can talk about the orthogonal complement, and it's simply defined as as usual. And this will be an n minus k Q code. And there's no, if I remember correctly, there's no obvious connection between the minimal distance of the dual code and the original code. I don't know, and it's probably you can tell more.
While in certain cases there are obvious connections, but not in general.
Not in general, yes.
Not in general.
Okay, so and it's important to highlight here that we cannot think of this orthogonal complement as in the natural sense in the real numbers, because here the intersection of those two guys could be huge. In fact, they could be equal, for instance, and in that case we'll have a self-dual code. Okay, and this in general, again, a linear code, since we're working with linear things again, we can describe a linear subspace with a basis, and this leads to the effective use of two descriptions of a code. The first one is called a generated matrix, and simply we take a basis and we form a matrix whose rows are that basis for C. So here you can see that those products here are all the code words. And actually this small a, is the piece of information that I was describing at the beginning. So we can recover the piece of information from code words and vice versa. This is actually the encoding. And we also have the parity check matrix, which is simply the matrix, a generated matrix for the dual code. Okay, and an important family of linear codes is the Hamming codes. And the Hamming code is defined as the code for which the columns of its parity check matrix form a maximal pairwise linearly independent subset. So we can describe, this is our definition, like that. From here, we can immediately deduce that n equals this number here, because that's the number of a maximal pairwise linearly independent subset in Q to the m. And additionally, well, k is well defined. This information rate is defined from n and k, and it can be proved that d equals 3. In this case, there's a characterization of the minimum distance in terms of the project matrix, which says that if the minimum distance of a code is equal to d, if and only if there are d linearly dependent columns, but no d-1 independent, there's one, sorry, there's one, what I'm saying. There's no, sorry, it's there are d-1 linearly independent columns, but if you take d, then if there's none, they are dependent. Yeah, that's what I wanted to say. So basically here, maximality implies this, because we have d-1 equals 2. That's what I wanted to say. Okay. So the parameters of the Hamming code can be deduced. So here we have 7 because it's 2 to the power of 3 minus 1. And here we have the dimension, which is 4, because it's 7 minus 3, and then 3, the minimum distance, because the thing that I was trying to explain. And then we have the dual of the Hamming code, which is called the simplex code. And again, we have the same length, 7, 3, which is 7 minus 4, and then this minimum distance 4. In fact, for the simplex code, we always have the minimum distance equals to q to the power of n minus 1. And here's a description of the matrices. This is the parity check matrix. So as you can see, here we have the weight 1, 2, 3, 4 for each row. So this is the minimum weight here. And for the binary case, all the columns are all the binary vectors in 2 to the m, non-zero binary vectors. And here's a generator matrix for the Hamming code. And as you can see here, we have the identity here and the identity here. So they are in row echelon form. And when you have them in this form, then you can simply take this square here, this matrix here, transpose it and put it here. And you can go from one to the other one and back and forth. And what else?
How can you say that the minimum distance is equal to 3 when you consider just H parity check matrix?
Yes. So you mean here?
Yeah.
Yeah. So basically, if you take those two, they are linearly independent.
Okay.
But if you take 3, they have to be linearly dependent. So, or what you want to explain?
Yeah, but well, I mean, by definition, what is the code word? I mean, the code word belongs to this code C, right? If you just look at the parity check matrix, what does that imply? That C times H transpose is equal to 0, all 0 vector, right?
Yeah, okay.
That's by definition.
Yes.
So what happens if you would assume that that the minimum distance is equal less than 3, sorry?
Mm-hmm. Well, I don't know. I don't know what you want to say.
Well, I mean, C times H transpose actually means that C is a code word and its non-zero coordinates chooses the columns of H, right?
Mm-hmm.
And in case if you would have a code word which is of weight 2 here, right? Then you would have the case that the addition of 2 columns gives you all 0 column, right? Which is impossible, right?
Yeah, because
yeah. I mean, okay. Yeah, of course. It's just a further explanation, kind of how can you see in H actually what is the minimum distance for this code immediately.
Okay.
Right? Yeah,
okay.
it's
Thank you.
pretty the same, but it's just
okay, just a further explanation. Okay, thank you. Okay, so after discussing this classic family of codes, of linear codes, I want to talk a little bit about this codes from query functions, and because they are useful for constructions. In our case, for our constructions, and in general, they are useful for recovering properties of query functions or vice versa. So from codes to functions and from functions to codes. And so we start with a query function is simply a function from this vector space to the base field here. And notice that if we take all the values here, then we'll get q to the power of n evaluations. So we'll get a vector here in this space if we consider the truth table of F. And typically we'll consider it ordered and some ordering. And usually it's lexicographic. And so we can have a vector uniquely determined. And also, we want to describe linear functions, and linear functions are given by the following construction. If fix a vector and then consider this function, which is the dot product of the vector with the input here. And this is linear because, well, it's the dot product. We're basically fixing one coordinate and we're running over the whole space. And so this is linear. And in fact, all the linear functions can be constructed in this way. And now we define the following linear code, which is the truth values, the truth tables of these values, which are the sum of F and the linear functions here. We also want A equals 0 because we want all the linear functions. So this set can be linear and also have a larger dimension, right? By considering this function. But we could get easily that if F is not linear, then this is a Q to the power of n plus 1 Q code. So the dimension here is easy to see because we have nonlinear things. So those are linearly independent and they induce, if we take a basis here, then we easily get the basis for this code. And the length is Q to the power of n because of this. I wanted to say something here that, yeah, the weight distribution of this code is closely related to the Walsh transform of the query function here. But as the dimension increases, the connection is quite blurry, okay? But for the binary case, we can explicitly state it. Another construction that I want to mention, and I just briefly touched this one, but we'll come back to it at the end of the talk. And this is a more general construction known as the set-defining method, introduced by Ding, probably, yes. And it works as follows. We take a multi-subset, whichever we want, from this vector space, and define the linear code as the entries of our vectors are going to be the dot product of the first entry here times a fixed vector, then the second vector here times this vector, the nth vector here times this vector, and then we run over the whole vector space. So from here we can see that the length of the code is n, and its dimension is at most k, and this code could lead to, by suitable choices, we can get interesting codes. And so, for instance, if we get the d equals to the support of f, then we could get a few weights or things like that, or well, interesting codes in general. And actually, the previous construction C sub f is a particular case of this construction here, by taking the defining set as the first coordinate would be the evaluation of f, and then we put all the vector x. Then we have n plus 1 coordinates here. So this is a subset of this space. And so, for instance, here, when f is linear, the code will have dimension n. So here, if we have f linear, then we'll get dimension n. So in this case, k minus 1, right? So that's why this is at most k. And we'll come back to this a bit later. Okay, so I want to talk about minimal code, and they're important in secret sharing schemes and signature and different applications, two-party computation, but originally they were meant to be for secret sharing. And I'm not going to discuss secret sharing here because I'm probably because there are a lot of things over there. So I just want to briefly discuss minimal codes. And okay, so we say that code word covers another one if and only if the support of the first code, the code word covers, it contains the support of the other code word. And we denote this relation by this. So actually we're ordering the code basically, say the multiples of C by inclusion. So notice here that this C always covers its multiples because the weight doesn't change. So the support doesn't change. It's the same. And we say that a code where C is minimal if that's the only case, if they cover only the span of C. Okay. And here's a depiction of this thing applied to the Hamming code. So in the Hamming code H23, we have 16 code words. And it turns out that those code words are minimal. All the code words here are minimal, except for the 1. And well, 0 can be minimum. Yeah, but by definition, we take non-zero code words here. And so as you can see, they form, and the minimal code words form an anti-chain in this order here. And there's a nice theory of posets related with minimal codes and with certain hierarchy ideals and things like that, and it's nice. But what I wanted to point out here is that this is almost minimal except for the 1. That's interesting, right? but we'll be interested in the codes that are minimal. So every code word, every non-zero code word is minimal. And okay, I'm gonna tell you some properties of these minimal codes. The first one is that by definition, they form a Sperner family. So by Sperner's theorem, we have that the size of the family is less than n choose n over 2. So here we have to subtract 1 because we're not counting 0, and then the multiples. So we can get this bound here for every minimal code. Also, the minimal codes are intersecting. And that means that if we take any two code words, their supports are not empty, or in other words, if their supports are non-disjoint. And if they are disjoint, if and only if one of those code words are the 0 vector. And it turns out that in the binary setting, an intersecting code is equivalent to minimal code. And in general, a minimal code is a q-1 intersecting code. So in the binary case, we have this characterization of codes. And some known bounds are this. The first one here, it tells us that the minimum distance is larger than the dimension plus the size of the field minus 2. So in the binary case, we have that the minimum distance is larger than or equal the dimension of the code. And the maximum distance satisfies the Plotkin's bound, actually. And no, the singleton bound, sorry. And this is n minus k plus 1. And so they're, in some sense, they're quite tight, the codes, because they cannot be, the code words cannot have large weight in a sense. And one example of minimal codes are the simplex code. And for every q, for every m, the simplex code is a minimal code. And okay, so, and we want to focus on a specific subfamily of minimal codes. But first, I have to introduce this sufficient condition for a code to be minimal, and that it's if the code words are close enough, let's say, because a code is minimal if this ratio here, the W min and over W max, is larger than q-1 over q. So this implies that the code words are close together. And well, a code satisfying this condition here will be called narrow, and otherwise it's gonna be wide. So we want, wide means that the minimum weight and the maximum weight are like 2 apart from each other, right? And well, in some sense again. And rephrasing this lemma, we can say that a narrow linear code is minimal. And surprisingly, there were no known examples of infinite families of wide minimal codes until the recent work of Heng and Zhou. And they used the following characterization, but they explicitly provided 3 examples of such families using a quite nice techniques. And this is a characterization of minimality over FQ. So a code is minimal if and only if we have this relation. Well, actually, this relationship doesn't hold for any linearly independent code words. So here we're varying over this the set of linearly dependent, this line, TV plus A. So the weight, if we take this sum, is not equal to Q minus 1 times the weight of A minus weight of B. So this is and this is a very strong result because we're characterizing minimality in terms of the weights. And using this, they were able to provide families of binary wide minimal codes. Okay. And in the binary setting, there are nice characterizations of minimal codes as well. So just Amar already talked about the wash transform of the Boolean function, but I'm gonna highlight it here. And so recall that the wash transform of the Boolean function is defined as this sum here, and we're somehow measuring how the f is related to linear functions. So that's kind of like the intuition behind this wash transform. And as you can see, this recall our code C sub f, then the wash transform are, and the wash values are related to the weights of our code. And there's this theorem, which says that for a non-affine Boolean function, the code is minimal if and only if the wash values satisfy this condition. So for every two vectors here, then those two values are not equal to 2 to the power of n. And this is a simple rephrasing of the previous characterization on weights used in the binary case. And okay, this will be our first characterization. Now, the second characterization is given in more geometric terms. So first, we denote as a bar and the complement of a subset, and a star the set with the zero removed. We say that we define a vectorial 1n-1 blocking set as a subset of this vector space here without the zero, intersecting all in such a way that intersects all the n-1 dimensional subspaces, so all the hyperplanes, but it doesn't contain any such hyperplane. And we say that this cutting if this intersection with every hyperplane is not contained in any other hyperplane. Okay, those definitions are better depicted here, or at least I think so. So here we have this potato here, which represents our blocking set. And for every hyperplane, it has to intersect this blocking set, but it cannot be contained. So we have somehow this, somewhat this picture. And it's cutting if we take the intersection of this hyperplane with this potato, then this thing here, which is the intersection, is not contained in any other hyperplane. So those are definitions. And recently, I think it was last year, Bonini and Borello gave a sufficient condition for code to be minimal, for our code, the CF code to be minimal. And it reads as follows. If we have that the support of our function, the complement of the support of our function with the zero removed is an n-dimensional vectorial cutting n-1 blocking set. Well, here n-dimensional means that the thing generated by the set is n-dimensional, so it generates everything. And if we have that for every non-zero vector, there exists an x such that this happens. So basically that this code word is not covered by this one. And those two conditions are sufficient to prove that C sub f is a minimal code. And in fact, there's a full characterization of minimality in terms of cutting blocking sets. So we can regard those two things as the same object under certain conditions. Okay, and we have time. Oh. Well, briefly, I'll describe the constructions. And here's a blueprint of our constructions. First, they're carried out in the binary setting. And we look for codes which are wide, so they satisfy this condition here. And in all our constructions, we proceed as follows. First, we find a kind of like stretch or wide structure, delta, where S, this union, where S has nice algebraic properties, and R takes care of the rest, okay? That's why R, rest. And those two things have to guarantee that the intersection with hyperplanes is non-empty, and those conditions that I mentioned before. And we consider CF, where F is the characteristic function of delta. And we apply one of the two conditions before to given before to get minimality. So either the Walsh characterization or the geometric condition, the cutting condition. And here's a mnemonic for us to remember quickly. So we have delta, we have C sub F, and we have WC. And this doesn't stand for water closet, but for Walsh characterization. And we have delta plus C sub F plus CC. And this is not carbon copy, but cutting condition. This is for us to remember, okay? And the first condition, the first construction is based on basis. So we take a basis and we take any set of cardinality at most 2 to the power of n minus 2 minus n, which is disjoint to A, and containing at least one point in this form such that the weight of those coefficients is even if we form the vector. And it turns out that if we take the characteristic function of this delta, then CF is a minimal wide code with parameters, with these parameters. And the proof simply is delta plus CF plus CC. So here we use the cutting condition. The second construction is based on n-2 dimensional affine subspaces. And here our algebraic structure would be an n-2 dimensional affine space with a point removed. And gamma, here, this is not R, but this R was just for us to have an idea, but here we have gamma, and gamma will be any set of cardinality strictly less than this disjoint to this set here, such that it intersects the unique hyperplane, well, actually the complement of the unique hyperplane containing A. And those are the conditions. And it turns out that if we take the characteristic function of the delta defined as this, then we again obtain a minimal code. And if we have one more condition here, then the code is wide. And well, the proof is delta plus CF plus CC. I need to go briefly to the third construction. And this third construction is based on hyperplanes and first we fix a hyperplane in a point not in that hyperplane. Then we take a subset, gamma, with cardinality less than 2 to the power of n-2, such that for every other hyperplane, this P0 is such that this P0 is not contained in that hyperplane, then this gamma is not contained in this hyperplane. And those are basically saying that we're intersecting every hyperplane. That's kind of the feeling of this subsets. And it turns out, again, if we take the characteristic function of delta, then the code is wide minimal and it has those parameters. So we have plenty of flexibility here from when choosing gamma. And it turns out, well, the proof is the same, delta plus C sub F plus WC. And well, those sets, it turns out that we can explicitly construct sets satisfying those conditions. And an example, I'll give an example of the third construction. And it's based on something called the root functions. First, we consider the affine function the full affine function, this one. So here, all the terms plus 1. We select a point, which is not in the support, and swap the value of this point. And then we swap the value for every other x, which is a distance 1 of p0. Here's a picture. So we start with our function, then we swap 1 bit, and we swap all the other bits, which are at distance 1 from this vector here, from the vector corresponding to this bit. And the resulting function is a root function of maximal weight, this weight here. And those root functions are useful for digital circuits and hardware testing. So, and using those root functions, we could prove that if we take this h and this gamma, using our third construction, we can get wide minimal codes with this minimum distance and this maximum weight or distance, right? And interestingly, if we take the limit when n tends to infinity, we have 1/2, exactly 1/2. And that's pretty interesting because we have a variety of codes satisfying being wide minimal, and such that it had their asymptotically behavior is exactly 1/2. Okay, and briefly, some open questions in future directions. The first one is to find precise relations, if any, between the 3 constructions. So how they relate in general. The second one is it'll be how to obtain better codes by applying certain operations, typical operation like shortening, puncturing. And the third one would be how to extend these ideas to a non-binary field. And the fourth one that I want to mention is in a rather different direction. And this was proposed by Ding very recently, and this year, and I think 1 month ago or something like that. And it's a fact that every code can be seen as C support of f for some function f using this set defining method. And this is a fact. So given a known family of codes, how to trace the functions f giving rise to those codes. So by using, I don't know, known families of codes such as Red-Miller codes, McDonald codes, Hamming codes, BCH codes, whatever, what the f looks like. I mean, it's a very interesting thing, and I think it's worth trying this, at least for some known families of codes. And I think that's it.
Thank you, René, for the nice talk. Are there any questions? Suggestions?
I can wait for your questions, and then I can pose some.
Mm-hmm.
Okay, of course.
No questions from the others?
Go ahead, Enes.
Okay, well, no. Okay, so it was a nice talk, but I think that you put so much details about the linear codes, which I guess that all the audience are familiar, because we are talking just about linear codes, right? So it's just a subspace, right, of something. And in the end, so you are kind of missing to mention. So you are just mentioning one paper that we had, that we submitted recently, right? But we have two stronger papers which are also submitted on this topic, which are really kind of nice and pleasant results, which maybe you should have touched in more detail as well. That's my kind of point here.
Okay, so yeah, I agree. I spent a lot of
everybody knows in the audience what is a linear code.
Sorry. The thing is that I was thinking about to give this talk for broader audience because of this crypto month and stuff. So we wanted to reach more people. That was my thought.
Okay.
But
Yeah, I agree on that.
I spent a lot of time there, so probably a shorter version would have been better. But I think that was my point.
Are there any students attending this talk, or that's just us?
No. There are other PhD students not working in cryptography or coding theory. So I guess it's such a.
Okay. Yeah. In that context, it is fine. Actually, but you should have mentioned that we have kind of more results, and these open questions actually a little bit to elaborate on Ding's recent result, which is kind of very interesting, because I just want to point out here that I mean, there are many subspaces, right? That's the point. And we want to find these minimal codes, which is a subfamily of linear codes. And even we want to find the optimal codes. What does that mean? It means if you fix the length of the code, right, and dimension, that you reach the maximum possible distance, right? And in such a case, the code is called optimal, right? And these codes are kind of recently obtained by Ding using band functions and these almost band functions, right? And other kind of these perfect combinatorial objects. And the Ding's question actually was, okay, so let us now study all these optimal codes, because it seems to be one-to-one direction between this defining set and this and these optimal codes. So we are kind of doing a backwards kind of research. So given an optimal code, how can I figure out what is this Boolean function in this binary case, which is the defining actually function of such a code? So this is a power of this defining set, because this defining set, it can be anything, right? And in certain cases, you get very bad codes if you pick up a certain subset of your set, of your space right there, and try to construct a code. But otherwise, you can get to these optimal codes, and then we translate. We go back, right, and try to figure out what is this Boolean function lying there. Is it a kind of a new class of functions or whatever, right?
Mm-hmm.
I hope that you could follow this importance of this, because we need to work more in this direction, and this is really kind of important. I mean, it is a short paper just pointing out that any linear code can be defined using this defining set. So actually, Boolean functions actually stand for all possible codes out there. That's amazing, actually, result. And well, so I think that in the near future, a lot of research will be done in this direction, and there are many kind of open problems, and especially because René didn't mention two recent works which are also kind of very nice, and in particular one paper gives the largest known kind of classes of these wide minimal codes known, actually, because we can play with so many parameters there that it is amazing. And we need to actually check what do we get with this shortening and puncturing, maybe some optimal codes, because the problem here is that if you go for large n, actually in our constructions, so n is greater than 10 or 11, so the length of your code becomes suddenly 10, it is 1024 bits of length, right? And then in most of the cases, you don't know actually what is the optimal code in such a huge, for such huge parameters, right? So, but I suspect that there are some clever ways to do this shortening or puncturing or whatever to get codes of shorter length and which are kind of probably optimal then. And that's a really nice research direction that we are going to consider later on. Okay, sorry for this lengthy comment.
Okay.
Yeah.
Any other comments, questions? Maybe we have time for a quick comment or question. Well, okay, if not, let's thank to René. René, thank you once again for your talk. And see you next week.
Ciao.
Okay, see you.
Bye.
Bye.